Hello, I'm Israel Vega. I'm presenting my project over Coulomb's law. I just finished presenting the one over the group part, but right now I'll be presenting the one of my individual section over my project and my final observations. So what I'll be talking about is a project I made or a problem that I made up using Coulomb's law. So here it is. We're given two charges, one with 3 nanocoulombs and one with -5 nanocoulombs. They're both 20 nanometers apart, and we have to find the distance r to reduce the attractive force by exactly 50%. And so in this problem, we have two particles, and we want to see um, what new distance we need to reduce the attractive force by exactly 50%. And this problem is relevant to this topic because it examines the student's understanding of Coulomb's law and evaluates how the distance changes with force. And it's important that we analyze this change because it's an inverse square law and it's not something that varies directly or just regularly inversely like many scientific laws. So here's some benefits of understanding this question. It allows students to evaluate how changing one variable affects another, and it forces students to employ unique problem-solving skills because one thing about this problem is that many textbook questions about Coulomb's law, it just wants you to plug in one number, substitute one, or maybe just rearrange the formula, but this one um requires you to use lateral thinking instead of just plain substitution into a formula. And then it also requires students to partially understand how the how this law varies inversely with the square of the distance. Righty. And one thing that I had to keep in mind while writing out this problem was that we have to consider the very small scale since we're dealing with particles. We have to consider how small these particles really are. So instead of having them in coulombs, which is very large, at 6.24 quintillion electrons, I made them nanocoulombs. And I also have to consider the distance. They're 20 nanometers apart instead of meters. And then the reduced output mainly just forces the student to notice how the input value changes one thing and how the whole formulas are related to one another and how the behavior and relationship really works. And this problem is actually really unique compared to other ones. Like I said before, this problem is more focused on conceptual variable change instead of plug and chug variable substitution, and it promotes lateral thinking over substitution. And this is really similar to what my professor does. He has us analyze how increasing or decreasing one variable changes another, and by doing this, you're analyzing how decreasing the attractive force, how it affects the distance between these two subatomic particles. This problem in itself is really unique because this is similar to what my professor does. He has us analyze how one variable change affects another. So for problems like this, you have to analyze how decreasing the attractive force, what it does to the distance in a given change. So right here's a diagram that I drew out in order to help you solve this problem. So you have one particle with a charge 3 nanocoulombs and another one with a charge of -5 nanocoulombs. They're 20 nanometers apart, and you want to find what the half of the force required to reduce, or the new distance between these two particles to make the force between the two particles equal to half. So this diagram just shows two different particles. I made sure to make them blue and red so you could visualize this. And then I also included all the empirical objective values inside of the equation. And the question mark shows what's being asked of the student and wants you to find the new distance in order in between them to find half of the attractive force between these two particles. And in order to solve this problem, it's important to understand the relationships and the constants in this relationship. So right here, I denoted Coulomb's law, F equals K times the two charges over R squared. F is the force, K is Coulomb's constant, Q is the charge of the particles, R is the distance between the two particles, And Coulomb's constant is given by 1 over 4 pi epsilon naught, and the units are Newton meters squared per Coulomb squared. And epsilon naught is given by the permittivity of free space, which is epsilon, and it can be written out as 8.8542 times 10 to the negative 12. And this quantity just shows how easily space allows an electric field to form inside of it. So think of it, imagine the electric force between the two particles. And then nano is times 10 to the negative 9 whenever you need to convert these units. And one thing you have to keep in mind when solving this problem is that you have to first substitute the given values into the equation that denotes Coulomb's law. You're given the distance and the two charges. And after that, you have to half the force and rearrange the equation similar to as you see right here in this graphic. You're going to rearrange it, and then you'll square root r squared to determine the distance. And this distance is always going to be a positive value because r squared within the denominator, um, it's always going to be the absolute value because the range of x squared is greater than 0. Ready? And then it's also a scalar value, and there's no direction unless you're working with the vector form. And right here's the correct solution. So one thing that you have to keep in mind is that remember it's going to be the absolute value. You have to ensure that the scientific notation is accurate. Right here I included some prefixes if you need help solving this problem. And the only unit that shall remain once you're done solving this problem should be meters. Upon doing all this algebraic manipulation and halving the force, you need to convert meters to Newton meters to get an answer of approximately 28.28 nanometers. And here's some more additional information I gathered. As I said before, Henry Cavendish, he was a scientist who applied an identical device that was a technical torsion device to determine the Earth's density. And both Cavendish and Coulomb used primitive devices where they had to analyze the device themselves instead of looking at a reading from a gauge. And they both approached precision using poor technology, which I think is really awesome considering how limited they were to their resources in the technology they had at this time. And here's something that I found interesting. Coulomb's law changes at a unique rate compared to other formulas because one inverse law that you see throughout science is there's a gas law that says that the pressure varies inversely with volume, and you use this in chemistry, but this is a direct relationship. However, Coulomb's law is it inverses with the square of the distance, which is something different, which I think is something cool. And so it kind of shows that the small gradual increments produce radical changes. And as a person who likes math myself, I think this holds mathematical and physical elegance. And this graphic right here kind of shows the elegance because it shows that as you increase it, the distance of it um, grows rapidly. And this this graphic itself kind of shows that it grows fast. And then even in Coulomb's formula, you can see in the denominator, if you rearrange it enough, the the denominator of the equation is actually the area of or the surface area of a sphere, which is actually really nice. And overall, what Coulomb's law is it's just a law that denotes the principle that like charges repel, opposites attract, and it also governs this relationship of how our universe is held together through these particles, through electric forces, and Coulomb's law is able to connect simple geometry to these forces that hold our world together. And then right here's all my sources, and I included an image of the journal I read, which I think is really interesting if you're trying to look at the application of Coulomb's law. Thank you.